Okay, so continuing on our discussion about bases, there is one thing that we should have noticed fairly early on is that a given subspace W can and does have many different bases. Okay, as we've seen in the previous example, this example here, for this W, we've exhibited two bases. One is a subset of the V's, the other is here. Okay, so there are certainly many different bases possible for any given W. Now, if you try to work out even more examples, you'll become somewhat convinced about the following statement. But any of these bases, or all of these bases, they all have the same number of elements. Certainly in the example above, this space W here has a basis that consists of 3 vectors, as this one, and the other basis that we found, which is a subcollection of the V's, also consists of 3 vectors. In fact, this is a very general phenomenon that requires some proof. So let's formulate this carefully. So W is again a subspace. Okay, and let's first of all, let's observe the following situation. Say B, I don't need that. Oops. Let's say you have a spanning set instead of bases, W1 through WP, the spanning set. Okay. And as you notice, I'm specifying that it has P elements. Then any set of P plus 1 or more vectors in W is linearly dependent. Okay. Okay, now let's first of all prove this. Now maybe we should first of all discuss the consequence of this. Again, let W be a base, a subspace, then any two bases of W have the same number of vectors. So put it differently, if V1 through VR, W1 through WP are both basis of W, then R is equal to P. Okay. Now proof of corollary. That one is fairly straightforward. Well, if you see that since V1 through VR is a basis, it's a spanning set. Okay. Right. So the theorem says that by theorem, any set of R plus 1 or more vectors in W is linearly dependent. Now, since W1 through WP is a basis, it's linearly independent. So it cannot have more than R plus 1, more than or more R plus 1 or more vectors. Right? So it cannot have more than R vectors, i.e., well, the number of vectors in this set W1 through WP is P, so P is less than or equal to R. Now, if you interchange the roles of the V's and the W's and run this argument again, you will get the other inequality by the same argument. We also get R less than or equal to P. And you have two numbers, one is less than the other and vice versa. So R is equal to P. And that's what we want. Okay. So because of the corollary, we can now make the following definition. Again, you have a subspace. The number of elements in any basis of W is called the dimension of W. Denoted by dim W. Okay. Right. So what we've argued so far is that any, for a given subspace, any basis would have the same number of elements, and that number is independent of the choice of basis, and is called, by definition, the dimension of W. Very well, except that we have to prove the theorem. So let's do that. Okay, so proof of theorem. For this, well, we just proceed as follows. Let's say we have a set S1, S2, Sm. Let's say you have a subset of W, like these, consisting of M elements. And let's assume that M is bigger than P. Okay, we make that assumption. And we want to show that this set S1, S2 through Sm is linearly dependent. That's what the theorem states. And for this purpose, well, we're going to have to study the linear combinations of these S's, say C1, S1, C2, S2, Cm, Sm, and we declare it to equal to 0. And we want to be able to find C1 through Cm not all 0 so that this equation holds. Okay. We want to find C1, Cm not all 0 such that for this to hold. Okay. Well, let's see. Because these S's, S1 through Sm, they are taken from W, and because W has a spanning set, right? The little w's form a spanning set of the big W. We can write S1 through Sm as follows. And they can be written as linear combinations of the W's. So let's see, S1 goes to A1, 1, W1, A1, 2, W2. No, I want it differently. A2, 1, W2. That plus a P1, WP. Say S2, A1, 2, W1, A2, 2, W2, AP2, WP, and so on. Finally, SM is A1M, W1, A2M, W2, APM, WP. Okay. So substitute this. And what we've done here is we've written the S's in terms of the W's. We can substitute these expressions back into the equation containing S. So substitute these expressions to here. We get something rather complicated. Well, let's write it down. So C1 A11W1 plus A21W2 plus AP1WP. Yes. Plus C2 A12W1 plus A22W2 plus AP2WP plus plus CP CM A1M W1 plus APM WP equals to 0. Okay. And now here comes the standard thing that we do, which is collect vectors that are parallel or proportional to the same given vector. In this case, W1. Terms with W1 should be grouped together. Terms with W2 should be grouped together. And terms with WP should be grouped together. Like that. So that will give us the following: C1A11 plus C2A12 plus CM A1M W1. Yes. C1 A21 C2 A22 CM A2M W2 plus C1 AP1 C2 AP2 plus CM APM WP equal to 0. Okay. Okay, so remember what we are trying to do is to find the C's not all 0 for this equation to hold, this one. Now what we've done is we've rewritten this equation in a more complicated equation like these. Now the observation is that for the above equations to hold, we can we can find a solution to the following system. Right, so this equation again is saying that some expression involving the w's is equal to 0. Right, the left-hand side is a linear combination of the w's, and I want that to be 0. And one easy way for that to achieve that would be to set all the coefficients to 0, and doing that will give me this system C1. Maybe I should change it now. A11 C1, A12 C2, A1M CM equal to 0, A21 C1, A22 C2 plus A2M CM equal to 0. Finally, AP1 C1, AP2 C2, APM CM equal to 0. Okay, so again, the unknowns are the C's. Right, the unknowns are the C's. And we like to have some of them, some of the C's not zero. So this is a homogeneous system with unknowns C1 through Cm and P equations. Okay. Now we have M unknowns. We have M unknowns, P equations in that system. M is greater than P by assumption. So that means we have more unknowns than we have equations. So by the previous discussion, since we have more unknowns than we have equations, the system has non-trivial solutions. Non-trivial solutions. And that's what we want, right? A non-trivial solution would be the C's, not all of which are zero, making the system hold, therefore making this equation true, thus showing that the S's are linearly dependent. Okay, that's it. Simple as that. Okay, now let's see if we can do some interesting examples. So so let's say we have a subspace. Oops. We have a subspace that is given as the span of 4 vectors. These 4. Okay. So W is the span of U1, U2, U3, U4 in R3. So find some bases and also find the dimension of W. Okay, that's a fair question. So let's think about how we do this. Well, I don't. One of the ways of finding bases that we discussed before is to look at U1 through U4 and find linear relations among them and using those relations to drop vectors, right? Another way of doing that would be to interpret W as the row space of some matrix, and then use row operations to get to reduce echelon form. Okay, we can do those. Let's see, we'll just do one case, let's say. we'll just find one basis using the row space approach. Right. For the row space approach, you have to transpose these vectors into row vectors and put them into a matrix. And then you pick suitable row operations to get it into reduced row echelon form, which in this case is the following. Okay. And now the answer can be easily read off. You have a basis that consists of two vectors, 1, 0, 4, and 0, 1, minus 2, and the dimension is 2. Okay, that's that's one way of doing things. Now, now let's discuss some properties involving dimensions. It's stated. It's in the properties are summarized in the following theorem. Suppose you have a subspace W and the dimension is P, say, then the following holds true. Any set of bigger than P vectors in W is linearly dependent. Okay, to any set of fewer than P vectors in W does not span. Three, any set of P linearly independent vectors in W is a basis of W. And lastly, any set of P vectors that span W is a basis of W. Okay. So the way to read this is that these four properties tell you that the number of vectors you have somehow can imply properties of these vectors. For example, for 3 and 4, previously the proper definition for being a basis required that you have your vectors are linearly independent. Linearly independent. Right, so being a basis requires to be linearly independent and spanning. But if you have the right number of elements in your set, that is the dimension, then being linearly independent or being a span will be enough. Okay. Now, proof of the theorem. Proof of 1. Well, let's see here. So P is the dimension, right? P is the dimension, so P is the, so you can find a basis consisting of P elements, and if you have a bunch of vectors, in fact more than P vectors, you have a vector that's, you have a collection of vectors that's more than the number of vectors you need for a spanning set. So by the previous theorem, your set of vectors must be linearly dependent. Okay. Now, so now for 2, W has a basis consisting of P vectors if the given set of vectors, that is the, this set, given set of vectors with less than P elements span W, spans W, then because this set has, because this set has fewer than P elements, your basis vector, which has P element, is forced by the theorem to be linearly dependent. Again, by the previous theorem, the basis is linearly dependent. Which is a contradiction, right? Because being a basis should be linearly independent. Okay, now move on to the next property. If you have P elements that are linearly independent, we want to say that these P elements must form a basis. We need to show that they do span. Okay. How do we see that? Well, you just take, for this we really do need to fix a notation. Say U1, UP, right, has P elements. And suppose this set is linearly independent. Okay. Then what we want to show is that it spans W. So let's take an arbitrary element W from big W. We want to show that little w belongs to the span of these U's. Okay. Now, by 1, we've already argued that since P is the dimension, if you have P plus 1 vectors, they must be linearly dependent. So the vectors U1 through UP plus W is linearly dependent. Okay. So they exist. Say A0, A1 up to AP, real numbers, not O0, such that A0 W plus A1 U1 plus A2 U2 plus AP UP equals to 0. Okay, good. So because by assumption we know that these A's are not all 0, but we can be more explicit to claim that A0 is not 0. And that is argued as follows. If A0 is 0, then the equation becomes, well, if A0 is 0, this first term here, A0W, drops out. The equation thus becomes A1U1 plus up to AP UP equal to 0. But because U1 through UP is linearly independent, we must have these A's being 0 in order for such a linear combination to equal to the 0 vector. So, well then, well, A0 is already assumed 0. Now all the other A's are forced to be 0, but the A's are not supposed to be all 0. So this is impossible. Therefore, we must have A0 not being 0. Well, how does that help us? I mean, a good thing about A0 not being 0 is that you can now divide by A0, and you can then solve from this equation for W. Then we get W, little w, to equal to A1 over minus A0 W U1, A2 over minus A0 U2, AP over minus A0 UP. So now this is in the span of the U's. And that's what we want to show. Okay, very good. Now, the last property is that, again, let's fix the notations. Last property requires that suppose we have P vectors that span. Okay, then we want to show that they in fact form a basis, or in other words, we need to show that they are linearly independent. We need to show that they are linearly independent. Okay, so how do we do that? There's essentially only one approach for deciding whether a collection of vectors is linearly independent or not. right? Suppose otherwise. Suppose suppose not. That is, we assume that these vectors u1 through up are actually linearly dependent. Then there exists a1 through ap real numbers not all 0 such that a1 u1 plus a2 u2 plus ap up is 0, right? Being linearly dependent assures that. Now, by reindexing the u's, we may assume that AP is not 0, right? One of them is not 0, one of the A's. So we can decide to change the indices so that the one non-zero A is AP. Then what we can do here is to solve for UP using this linear equation. Get UP to equal to A1 on negative AP, U1 A2 on negative AP, U2 AP minus 1 on negative AP, UP. Okay. UP minus 1, sorry. So since U1 through UP spans W, and we've written UP as U1 as a linear combination of U1 through UP minus 1, we see that in fact U1 through UP minus 1 already spans W. Okay. Now, so what does this mean? This means that the dimension of W, means that the dimension of W is no more than, is less, or no more than P minus 1, right? What we have here is a collection of P vectors that spans W. So we know that a subset of these vectors form a basis of W. You know, that subset has number of elements being no more than P minus 1. However, the dimension of W is assumed to be P, which is strictly bigger than P minus 1. So that's a contradiction. And it contradicts the assumption that the collection U1 through UP is linearly dependent. So then, therefore, they must be linearly independent. Okay. That's the proof. Very good. Now, Now let's consider the following situation. So the case of a matrix, right, we've seen for a given matrix A, say of size n by n, we've seen a couple of subspaces associated to it, right? So from A, we get its null space, n of A, which by definition is the collection of x's, so x's in Rn with A satisfying Ax equal to 0. Okay. Now it's a subspace, so it therefore has a dimension. The nullity of A is this dimension, according to definition. Okay. We also get its range. And the range is defined or denoted by R of A. Defined to be what is it? The collection of all vectors y in Rm such that y is equal to A times x for some x in Rn. Okay. I should probably mention that this null space is a subspace of Rn, while the range is a subspace of Rm. Okay, the range is a subspace, so it's definite. We can consider its dimension, and the dimension of the range is called the rank. The rank of A is the dimension of the range. Okay, so there is another interpretation of the range of A, is the column space. Which by definition is the span of column vectors of A, right? By the same token, we can consider the row space. You also get the row space of A row space. Well, for this purpose, its dimension doesn't really have a terminology, at least for as far as we are concerned. Its dimension doesn't have a name. Okay. Now, let's see. Let's consider an example of these of a matrix A, and a concrete example, and look at these quantities. That is nullity, rank, and the dimensional row space. So okay. All right, so suppose this is our A, and what are we supposed to do? We need, well, there's one thing that's easy to see is the row space, right? If we perform row operations to A, we will not change the row space. Then if we end up reaching the row echelon form, reduced row echelon form, we can read off a basis, hence the dimension of the row space by just finding the non-zero rows. So we can do that, and let's take some time to do this example in details. R2 plus R1. R3 minus 2R1. 1, 1, 1, 2. R2 plus R1, 0, 1, 3, minus 1. 2 minus 2, 0. 4 minus 2, 2. 8 minus 2, 6. 5 minus 4, 1. Yeah. Okay. Now we proceed. R1 minus R2. R3 minus 2R2. Keeping R2. Like that. Oops. R1 minus R2, that's 1, 1, 0, minus 2, 3. R3 minus 2, R2, 0 here, 2 minus 2, 0. 3, 6 minus 6, 0. 1 minus negative 2, 3. Okay. So now we should, right. Now we should do 3, 1/3 of R3. R3, yes. R1 minus 3R3. R2 plus R3. And that'll give us this. R1 minus 3R3, 1, 0, negative 2, 0, 0, 1, 3, 0. Okay. All right, so now we get to reduce row echelon form. Oof. The leading ones are here, there, and there. Right? We see that all rows are non-zero rows. So the dimension of row space is 3. Okay. Now what about range? What about nullity? Again, by definition, nullity should be the dimension of the null space or the kernel, right? So that requires that to find the kernel, we need to solve the homogeneous system AX equals to 0, right? But the process of solving that system is to do row operations to the augmented matrix. But as you can see here, the matrix, most of the operations is here already in the processing of A. The augmented matrix differs only by adding one more column, the 0 column, to the very end. And that, the whole process will not change that column, so you just end up getting this system with zeros here. So the augmented matrix, so for solving AX equal to 0, we have the augmented matrix 0, 2 minus 3, 5, 0, 0, 0, and that just turns to, 1, 0, 0, 0, 1, 0, minus 2, 3, 0, 0, 0, 1, finally 0, 0, 0. Okay, so you can then read out the solutions. What are the solutions? Solutions are, or rather, the equations are x1 minus 2x3 equal to 0, x2 plus 3x3 equal to 0, and x4 equal to 0. Okay, so that's saying x1, x2, x3, x4 is equal to 2x3 minus 3x3, x3, 0. So that's x3 times 2, negative 3, 1, 0. Okay, so this is the vector form of solutions. You can certainly see that it has infinitely many solutions with one free variable. So the null space, in fact, has the following description. It's the span of a single vector. So the dimension of the null space is thus 1. Okay. Finally, the range. The range requires a little bit extra work, right? Because we have to let's think about how we do this. Right. So yeah, there's one thing. In fact, we've more or less done that already. So to find the rank of A, we exhibit a basis for the range of A, which is the column space of A. And we've seen several ways of exhibiting basis for say column space. Namely, we can just find, we can try to do that by finding linear relations among column vectors. Okay, the column vectors are well, this guy's 1, minus 1, 2, 1, 0, 4, 1, 2, 8, 2, minus 3, 5. Right, these four vectors, we know that these four vectors span the range. We just need to find linear relations so that we can use to eliminate the redundant vectors. But we've already dealt with that because the linear relation among the column vectors is this equation AX equal to 0. And we found all the possible x's here. So in particular, we can get, not in particular, we essentially have only one non-trivial linear relation. That is this one, 2, 1 minus 1, 2, plus negative 3, 1, 0, 4, plus plus 1, 1, 2, 8 equal to 0. Okay, and now the point is we can, for example, eliminate this highlighted vector in terms of by expressing it in terms of the other two vectors. Therefore can be or rather therefore we can view this as redundant. Okay, and that just means that we only need these three vectors for a basis. So therefore the dimension of the range is 3. Okay, and all right, so now there are two observations I want to make. They're a bit well, they're not hard to make. That is the dimension of the row space of A is 3, as we've established. This is also the dimension of the range. If you now add the dimension of the null space with the dimension of the range, you have 1 plus 3, that's 4. And the number 4 appears here. It's the number of columns of the matrix A. And there are some very general statements that you can derive from this, but we will do that in the future. There's just one more thing that I want to state. Before we end today's lecture, is that if you look at Rn is a vector subspace, certainly. Therefore, it has its dimension. That dimension is n, because you have the unit vectors forming a basis. And the unit vector has n such. Okay. All right, so that's the end of this lecture.